In this video, we're going to look at a typical work energy and power question. Is it a past exam question paper? Unfortunately, I can't remember which exam I took it from. It's a worksheet that I gave to my own learners, and it is question 8. So, they tell us the emergency services received a 911 call. That's obviously America. That building 2 over here is on fire, and the people were trapped inside a window. The emergency service dispatched a fire truck, but Spider-Man, the local superhero, intercepted the call because he's a superhero. He rushed to the scene of the building and arrived at building 1 before the fire truck. So we've got this scenario. Spider-Man has a mass of 70 kilograms, so here's my Spider-Man, 70 kilograms, and is initially at building 1 on the right. He spins an inelastic spider web, so it's not going to stretch, to platform B in order to swing to window C. So he's going to swing round like that. This is a pendulum. That means that you can't use equations of motion. They don't have to tell you that you can't use them. You need to know that you can't use them. Okay, that's very important. So, no equations of motion. It's not even an option. Okay, it's something you should know. Why can't we use equations of motion? Because equations of motion are for linear motion only, and this is circular. Then he swings, so he starts at 30 meters above the ground, so that's my initial height. He spins, I said that, which is located, there we got C, I'm just getting myself all confused here, and he swings to window C, which is 8 meters. It says, ignore the effects of air friction and accept that no loss of mechanical energy occurs. So we have conservation of mechanical energy, very important. He swings with an initial velocity of 0. First question, determine the potential energy of Spider-Man at window A when he's located stationary. So, we want EP. EP, and I didn't leave myself enough space, is mgh, so it's 70 times 30. No, before we do the times 30, do the times 9,8, because that's a constant, times 30, and we have 20,580 joules. Great, we know EP. Then they say, and that should say mechanical, state the principle of conservation of mechanical energy. Please be careful with this definition. It's going to be very tempting to go, energy cannot be created or destroyed, but simply transferred from one form to another. That's the conservation of energy in general. Here I'm specifically asking for mechanical. So, easiest way for this is the total mechanical energy in an, very important words now, isolated system remains constant. You can also say is conserved, okay? But the point here, though, is that it is an isolated system. Okay, it's got to be closed. Now they ask you, if Spider-Man reaches window C with a speed of 10, calculate the height h in meters of window C from the ground. Again, I don't think I left myself enough space, so I'm going to draw a diagram. Okay, so we have h, that's the height we're going to, that's at C. He started at A, which was 30 meters above the ground, and initial velocity was 0 meters per second, and he swings. We have no energy being lost to anything, okay? I told you we cannot use equations of motion. They have just asked you for the definition of conservation of mechanical energy. I want mechanical energy to be used. So the mechanical energy at A is equal to the mechanical energy at C. They also told you that he reaches C. They told us somewhere? They actually don't. When he gets to C, they do tell you. I've just lost it somewhere in. There we go. See, it's important to read, and this is why I like to write all over things, so I don't lose information. When he gets to C, his velocity is 10. Okay? So, mechanical energy at A is the potential energy at A plus the kinetic energy at A, which will be equal to the potential energy at C plus the kinetic energy at C. You've already worked out the potential energy at A. You don't need to do it again. That was the first question. So we know it's 2580. If you got A wrong, but you carry it down to this, you'll get the marks. Don't stress. However, he wasn't moving at A, so his kinetic energy is 0. Potential energy at C. I'm just writing this out like this. I'm not doing the straight substitution, so you can see where I get the information from. So this is 2580. He's 70, 9,8, and I want C. Again, 70. V now is 10. You've done the hard work. Now it's just solving for H. That's all you need to do. So H is 24,9 meters. Okay, I'm going to leave the maths up to you and trust that you can do it. Alright, getting to the maths is going to cost you 1 mark if you can't get to that final answer. Okay, great. The fire truck eventually arrives at building 2. So now we know the height for building 2 that we're going up is 24,9 meters. Uses a water pump to extinguish the flames. The water pump converts kinetic energy to hydrodynamic energy. Don't stress about what we mean by that. All we're doing is we're making the water move. Okay? If the water converts 4,8 times 10 to the 5 joules of energy in 2 minutes, what's the power of the water pump? Well, I've got how much work gets done in the time it's being done. So for 8.4, power, which is work, over delta T. So I have 4,8 times 10 to the 5, 2 minutes, so 2 times 60, has to be in seconds, and we're going to get 4,000 watts. Please don't convert to kilowatts unless you're asked to. What is our SI unit? Then they say the water is pumped at a constant velocity of 10. Determine the magnitude of the force generated by the water pump. Well, I know the power of the water pump. I now know the constant velocity the water goes at. That means I can use the fact that average power is force times average velocity. 4,000 watts. We want force. Probably should make it a bit bigger. Times 10. So the average force that's being applied is 400 newtons. Magnitude, I don't need a direction. Again, one step at a time. Don't panic when you do these.